In this video, we're going to look at some techniques for computing limits. In the previous section, we looked at finding the right-handed and left-handed limits. And if we look at some linear function, any function f of x that's linear, we know it's going to be in the form of y equals mx plus b with a slope and a y-intercept. And if we pick any particular a value, as x approaches a from the left, our function is going to be approaching some point at a, f of a. And as we approach from the right, as x approaches a from the right, f of x is still approaching this point a, f of a. And this is going to be true for any linear function. Now keep in mind, we're just talking linear functions here. And so since that's true for every linear function, we can say that the limit of f of x, assuming that f of x is a linear function, as x approaches a, is going to equal f of a. And so to find the limit, all we have to do is simply substitute in a. Let's look at an example. Let's say we have some function f of x is equal to 3x minus 1, and this is a linear function. It's in the form mx plus b, and we want to find the limit as x approaches 2 of f of x. Well, to find that limit, we were just shown in the last slide that that limit is simply going to equal f of 2, and f of 2, plug that in, we get 3 times 2 minus 1, and that's 5. So the limit of f of x as x approaches 2 is 5, because the function is approaching 5. In fact, the function is defined at 5. In addition to that, we have a set of limit laws here. And all of these are true for any type of limit we have. And so they're laid out here in the 7 different laws, and we're going to use these. And they're not quite as complicated as they may seem. They're actually quite simple. Basically, the sum law is just saying that if you have two functions, f of x plus g of x, so in our last example, that could be 3x minus 1. We have one function, 3x, and the other function, negative 1. And so since we're combining those, to find the limit of that composite of those two functions, or that sum of those two functions, is simply just going to be the limit of the first function plus the limit of the second. We can split that up into two separate limits. All right, well, same thing happens with the difference and the product and the quotient. And this constant multiple just means if we have a constant times some function like the 3 times the x, we can just pull the constant right out front and just take the limit of that original function there. And same thing happens with the power for if we have, say, x squared. Well, we could just take the limit as x approaches a of x and then square the number at the end. And this last one here I want you to look at, though, number 7, is a fractional power. Now, if we're raising to a fractional power, like a 1/2 or a 2/3 or something like that, well, we can do the same thing we did in Rule 6. However, we want to make sure that f of x is greater than 0 for x near a if m is even. Okay, now why is that the case? Well, if m is even, that means we're taking a square root or a fourth root or sixth root, so on and so forth. And so we can't have a negative radicand when we're taking even roots. So that's why f of x has to be a positive number for any m that's even when n divided by m is in its reduced lowest term. Now, I'm not going to take the time to prove these right now. In fact, we'll prove Law 1 later in a future section, but you can just use your intuition to see that they make sense and take my word for it that they actually do work. Let's look at an example that uses those laws and also kind of shed some light on a future statement that we're going to make here in a moment. Let's just take an arbitrary function. It doesn't matter. Let's say f of x is equal to 7x cubed plus 2x squared minus x plus 3. Okay, and let's take the limit of f of x as x approaches, and let's keep it arbitrary, and let's just say a. All right, now a could be a number, it could be any number, it doesn't matter, but let's just leave it as a. Well, according to our previous rules here, since we're adding these terms and subtracting, we can rewrite this. This can be 7 times the limit of x as x approaches a, and then take that and cube it, plus 2 times the limit as x approaches a of x, take that and square it, minus the limit as x approaches a of x, plus the limit as x approaches a of 3. Okay, so we broke that up. Now, in all honesty, I'm not going to require you to do this and actually write these out, but I'm doing it now just to demonstrate it and so you can see it visually. And then really you're going to end up doing things like this in your head. And so what this allows us to do is we can break things up piece by piece. Okay, well, the limit of x as x approaches a is simply a. So this is 7a cubed plus 2a squared minus a plus, and what is the limit of 3 as x approaches a? Well, 3 is a constant. 3 stays 3 all the time and has no dependence on x, so therefore this is just 3. Okay, well, what do you notice here? This is simply f of a. So we said that to evaluate a linear limit, or a limit of a linear function, all we have to do is just plug a in. Well, this is not linear, this is cubic. But this is, however, a polynomial, and so this leads us to our next theorem, Theorem 2.4, in that whenever you have a polynomial function, the limit of any polynomial, it could be cubic, quartic, quadratic, quintic, whatever you want, any polynomial function, the limit of that function as x approaches a is simply that function evaluated at a. And so this is a big important theorem here. And so any a value, doesn't matter. All we have to do, the limit as x approaches that value, plug it into the function, and we see what the limit is. Well, the same sort of thing happens with rational functions as well, as long as this does not equal 0. We can't have a 0 in the denominator. So provided that a does not give us a 0 in the denominator, then we're good. We can just plug it in. So any polynomial or rational function, you can evaluate the limit by evaluating the function at that a value. Now let's look at another function, a function that's not linear, not polynomial, not rational. Let's do a piecewise function. Everyone loves a good piecewise function. So let's say f of x is equal to negative 2x plus 4, and you might say, wait a minute, isn't that linear? Yeah, it is linear, but that's only part of it. Negative 2x plus 4, and let's say that's when x is less than or equal to 1. And let's say it is equal to the square root of x minus 1 for x greater than 1. Okay, so we want to find, well, if we want the limit of this function for any a values less than 1, then we just plug it in. And any a values greater than 1, we just plug it into this part. But what about as x approaches 1? We want to know what is that limit. So let's look at the graph first and see what we have here. Well, the graph shows a linear piece to the left and this radical piece to the right. And if we evaluate the left-handed and right-handed limit, the left-handed limit as x approaches 1 from the left, we're approaching a value of 2. And as x approaches 1 from the right, we're approaching a value of 0. So our two one-sided limits are defined as 2 and 0, so this tells us that the limit of f of x as x approaches 1 does not exist because our one-sided limits do not agree. Since these two are not equal, the limit does not exist. Let's look at another special case here. Let's say we have a function that looks like a polynomial, but there's one little change here. At some value a, we have a hole, and maybe we're defined somewhere else here. And so the limit as x approaches a of f of x does not equal f of a. And we see that the limit does in fact exist, because as we approach from the left, we're approaching some value here, whatever that value may be, we'll just call it b. And as we approach from the right, our function is approaching that same value b, but it's not the defined point for the function at a, because we're defined up here at some other point. All right, so it's important to see that the limit does exist, but it's not f of a. All right, now let's have the same graph and just get rid of that point. We see that our function is undefined at a, however, the limit still exists. The limit is still whatever this y value may be, and if we're calling it b, then we'll just say it's b. So the limit of f of x as x approaches a is still that value b, whatever it is, but our function is not defined there. And I'll give you another example here of how that works. Let's look at the function f of x equals, and let's say it's a rational function, x squared minus 6x plus 8, and that quantity is being divided by the polynomial of x squared minus 4. All right, and let's say we want to look at the limit as x approaches 2 of f of x. And you might say that, okay, this is a rational function. Theorem a little bit ago says we could just plug in 2 and evaluate. But here's the issue. When we plug in 2, we get a 0 in the denominator, and we can't do that. All right, so if we look at this graphically, and if we look at the graph here, we see that here's the function. This is the ideal function. Now remember, if you plug this into a graphing calculator, it's not going to give you what you see on the left. It'll give you what you see on the right, and I'll explain in a moment. But we have this graph with a hole at 2. But we can see, just by looking at this, that we are in fact approaching a value. Our limit is going to exist, because as we approach from the left and the right, we're approaching this same value here. And from the graph, you can kind of infer that, oh, looks like it's negative 1/2. But let's look at this analytically as well and say that this graph is simply y equals x minus 4 over x plus 2 with a hole at that point. Now, where did we get that? Let's go back to our function and let's factor this function. Well, if we factor the top, the top can factor into x minus 2 and x minus 4. All right, and if we factor the bottom, it is x and x plus 2. And we notice that the x minus 2's cancel, and we're left with the function x minus 4 over x plus 2. And so this original function f of x acts just like the rational function of x minus 4 over x minus 2 while maintaining the same domain of all reals except for negative 2 and positive 2. So we're still undefined, but we just we still act like this rational function. And looking at this rational function, if we were to evaluate the limit as x approaches 2 of the x minus 4 over x plus 2, we can plug 2 in. That doesn't give us an issue. It doesn't give us 0 in the denominator. So when we plug 2 in, that gives us 2 minus 4 over 2 plus 2, and that's a negative 1/2. And that's where we get the negative 1/2 for our limit. Even though when we looked at the rational function, the function didn't exist at that point, the limit still does exist. Now we're going to look at some other special cases in class with this section, and we're not going to look at any more in this video here, but there are other special cases that we're going to deal with and some ways that we can get around getting that 0 in the denominator.